All right, we're going to take a look at these midterm practice problems. So the first one, did I say midterm practice problems? I guess that's what it says at the top of the page. So the first one says, it says, hey, we want a student applies a 200 Newton force horizontally, pushing a 25 kilogram block so that it slides up a ramp at 3 meters per second. And they have a little picture for you. I can see that they give you the angle of the incline. So here's what the picture looks like. Right? And there's that crate. And there's a person who's shoving on the crate. Oops. Anyway. And they show you that force from the person, they label it force of push. They show it going straight sideways. Okay. And they've told us that that force is 200. And they've told us that this angle down here is 20 degrees. And they've told us it's a 25 kilogram block. You say, well, because it's kilograms, you know that's the mass, right? That's not a force. So I can say the mass of the block is 25 kilograms. And they tell you that it's sliding uphill at a constant 3 meters per second. And what we're going to do with that information, you say if it's constant speed, that means it's in equilibrium, and that means the forces should all balance in every axis. And so that's what we get to start with. They'd like us to, draw the free body diagrams, write the sigma F equations, and solve for every force acting on the block. So here we go. So run through our steps. You say, well, the first thing I need to do is my system is going to be just the block. You choose the system. Now I'm going to go ahead and do my force diagram, my free body diagram. So I'm going to represent the system simply. So I'm just going to represent it. You can represent it as a dot or a box, or if it's something round, use a sphere, like a sphere or something, or a planet, I'll use a circle. But in this case, I'm going to use a box. It's important that I'm going to draw this box in the orientation it is in the problem. That is, we're not going to try to straighten it out or anything. We're going to leave it like it is. All right. I think in math class when they teach you vectors, they sometimes teach you to straighten it out. So okay, so let's run through our forces. We have a sequence of questions that we run through to make sure that we get all the forces acting in our system. We don't leave any out. And by the time you're done with this question, you've got it all. So the first thing we do is we ask about ranged forces. Remember, the only ranged force we're working with this semester is the gravitational force. There's also electromagnetic, strong nuclear, weak nuclear force. We're not going to study the nuclear forces this year. Electromagnetic is next semester. So we just have gravitational force. I'm going to go ahead and say, for gravitational force, there has to be a very large, massive object. Either that's your system or that's near your system. And in this case, you say, yeah, there is a huge, massive object nearby, and that's the Earth. And so there'll be a gravitational force between the Earth and the box. Gravitational forces, we always represent them as going from the middle of one object to the middle of the other object. So I want to draw my forces going from the middle of the box to the middle of the Earth. Well, that means straight down, right? So I draw my gravitational force from the center of the box, going straight down towards the center of the Earth. I'm going to label that gravitational force, F sub g. Now we go to contact forces. Okay, that was it for range. Contact forces, there's 3 types of contact force that we typically deal with. Those are normal, friction, and tension forces. So because those are contact forces, things have to be touching to have a contact force. So first, I just list everything that's touching my system. In this case, there's 2 things touching the system. There's that ramp and there's the person. Okay, so first we'll start with the ramp and we'll run through our questions for the ramp. First question, are those surfaces being pressed together? If they're being pressed together, there'll be a normal force. You say, yeah, look, the gravitational force is shoving that box into the ramp, so the ramp will push back with a normal force. Normal forces always go straight out of the surface. They're perpendicular to the surface. Geometry slang for that is they're normal to the surface. That's why they're called normal forces, because they always act perpendicular to the surface. It's not because they're common or usual or regular. They're called normal because they're perpendicular to the surface. So it's going to go straight out of the ramp. Yoink. There's my normal force. Okay, on the box by the ramp. And now you say, once you have a normal force, the next question you ask is, are those surfaces trying to slide past each other? Because if you have to have a normal force before you can have a friction force. If they're trying to slide, there'll be friction opposing the slide. In this case, it is in fact sliding uphill. And so there must be a friction force going downhill, opposing the slide. That's happening along this surface. And so I'll write my friction force. It's a kinetic friction. You can put a little subscript K on it if you want to show it's kinetic friction, because we're sliding. Static is when it hasn't slipped yet. And that's it for that surface, right? The other thing touching it is the person. And he said, so you could run through our questions and say, are those surfaces, the person and the box, being pressed together? And you'd say, yeah. And that would give you a normal force going straight out of that surface, like this, yeah? And then he'd ask, are those surfaces trying to slide past each other? In fact, you can imagine if a person's hands are on the box, their hands would tend to want to slip up that surface. I'm sorry, I apologize. Their hands, if they're pushing straight that way, would tend to slip down the surface. There'd be a friction force up on the hands, or third law, down on the box. So there'd be a friction force going this way along the surface. So there'd be a combination of a normal and a friction. Well, in this problem, they just gave you the combination of both of those together when they gave you this force push. That's really just a combination of a normal force and a friction force from the person. What we're going to be doing here, so I could represent that as two forces, but they already gave me it together and they gave me the value for it. I'd much rather use what they gave me. From like a problem-solving perspective, why would I want to invent two variables, friction and normal, right, from the hands on the box, when I could just have one variable, force push, right? So from a problem-solving point of view, it makes sense to just stick with this one force, okay? When we do this, we sometimes call this an applied force, is what they call this. And usually it's like a person pushing on something. They'll just give you the total force from the person. You're like, okay, that's an applied force there. I'm just going to use the name they gave me, force push, and I'll put it on my diagram. It's a force going straight sideways, right? Straight horizontal. That's that force of the push. Okay? And that's all my forces then. Okay? There's nothing else touching it. If there's any ropes or strings or wires being stressed, I'd have tensions, but there's none of those. So that's it. I've run through my questions for each thing touching my system. I have all my contact forces. We're done. All right, the next step in solving is to choose coordinate axes. We know that it's easier to think about things being in equilibrium or not equilibrium to analyze forces instead of all of them at the same time. Just look along one coordinate axis at a time and see if the forces are balancing this way and balancing this way. Right? And so that's what we're going to do. So we're going to choose axes. Now we have a rule for which way we make our coordinate axes go. The rule we've been using is the first coordinate axis always goes along the direction of the motion. And then our other axes always make right angles to that. If I have something that's not moving at all, then technically I can use whatever coordinate axes I want. Although it's usually traditional to do up and down as your first one. And that makes sense because that way at least the gravitational force won't have to get split into components. But in this case, we're moving along the ramp. So we'll have our first coordinate axis go along the ramp, parallel to the ramp. Okay? And the other axis will go perpendicular to that. It's traditional in physics textbooks and such to still call these axes X and Y. But I think it's a better description and easier to talk about if we instead call them the parallel to the ramp axis and the perpendicular to the ramp axis. I think that makes a lot more sense and it's easier to think about. It also avoids another little problem that can happen if you call them X and Y. So we've got our axes. I should choose which direction I want to call positive. Now, when you choose directions on axes, if you have like left, right, up, down, it's kind of traditional to call right and up positive. But technically, you can do whatever you want as long as you let people know. So in this case, I think I've got my directions uphill and downhill and out of the ramp and into the ramp. I think I want to call uphill positive because that's the way it's moving. Let's just do forces in the direction of motion. So I'm going to call uphill positive. And then I got to decide out of the ramp or into the ramp. I'm going to call out of the ramp positive. So in other words, I'm calling these the positive directions, uphill and out of the ramp. Okay? Any forces now that are pushing along multiple of these directions have to get split into components that just go along these directions. So I can see that this normal force goes straight out of the ramp. That's going in the out of the ramp direction. That doesn't have to get split up. I can see this friction force is going downhill. It's in the downhill direction. That doesn't get split up. But this force of the push, I can see it's going straight. It's going which way? It's going, using the words uphill, downhill, out of the ramp, into the ramp. It's going uphill and into the ramp. So I have to replace it with a chain of arrows that are going uphill and into the ramp. So here's my uphill, and into the ramp. So those are the components of this force push. I'm going to rewrite force push so it's at the hypotenuse here. My right angle is always between the components, right? Okay, I'm making sure I'm putting arrowheads in my components because we care about what direction these are in. Okay, hey, this angle of the hill, that 20 degrees, that's going to be one of the angles in this triangle. You say, I know that looking at this right triangle, I've got this angle and the complement of that angle and 90. You say, hey, this one's skinny and this is a bigger angle, skinny angle, fat angle. You say, hey, look, skinny angle, fat angle. This one's the 20 degree. And that makes this side the adjacent side, this side the opposite side to that angle. So the adjacent side here, I'm going to use cosine function. Since we know the cosine of an angle is the adjacent over the hypotenuse, I know the hypotenuse is F push. This is the adjacent, the side, the leg touching it. I'm going to use cosine. If I'm trying to find that adjacent side, I'm just going to rearrange this, get adjacent by itself, and multiply both sides by hypotenuse. Hypotenuse times the cosine of the angle would be the adjacent. So in this case, that would be the hypotenuse is F push, and the angle is 20 degrees. That would be this side. So I'm going to label this side F push cosine 20. Sorry, that's really sloppy. Okay, F push cosine 20. All right. This side, on the other hand, is the opposite side. So by a similar argument, this will be F push times the sine of 20. Point is, it's not just cosine and just sine, it's the hypotenuse times the cosine, the hypotenuse times the sine. Okay, hey, what about the gravitational force? You say, is that going, what direction is it going? And you'd say, hey, it's going both into the surface and downhill. So I have to replace it with components going into the ramp and in the downhill directions. Again, my right angle is always between the components. There's a tendency among people to want to go perpendicular and then just straight sideways, but that's not one of our axes. Our axis is along the ramp. Right angle is always between the components. Hey, look, skinny angle, fat angle. The skinny one, that's this angle, 20 degrees. Hey, how long is this side? That's the side that's adjacent, so that'll be the hypotenuse, FG, times the cosine of 20. This is the opposite that angle, opposite leg, so that'll be the hypotenuse times the sine of 20. Okay, I now have all my components labeled. Okay, and that's it, okay? Sometimes we ask you to go ahead and identify any forces that are congruent to each other. Let's see if we can come up with any congruencies in this one. In this case, we know the system's in equilibrium, right? So let's take a look. We're going to look at each axis and look at the forces in those axes and see if any of them we know balance out. So if we go along the parallel to the ramp axis, how many forces do we have going along the ramp? You say, look, here's F push cosine 20 going uphill, and here's F friction going downhill, and here's FG sine 20 going downhill. So we've got three forces in that axis. If there's three, they have to add up to 0. I can see that this one going uphill is going to be balanced by these two going downhill. But I can't like set any, doesn't mean that, and none of them have to be specifically equal to each other. It's this combination of these two are equal to that. I don't have a way of showing that with congruency marks, so I'm done. What about this axis? How many forces in this axis? Well, I've got this normal force going out of the ramp. This is the perpendicular of the ramp axis we're talking about. Normal force going out of the ramp, this component of gravity going into the ramp, this component of that force push going into the ramp. There's three forces in that axis. Normal force pushing out is balancing out these two forces pushing it into the ramp. Again, I don't know specifically that any of them are exactly equal to each other, so I can't make any congruency marks for that axis either. So it turns out that we don't have any congruency marks to make on this diagram. Okay, what's our next step? The next step is to go ahead and plug into sigma f equals 0 for systems in equilibrium. How many sigma F equations can we write? We can write one equation for each system for each axis. So in this case, I only have one system, this box. So I can write a sigma F for the perpendicular axis and a sigma F for the parallel to the ramp axis. So here we go. I recommend writing these horizontally, like next to each other. Some of the forces in the parallel to the ramp axis is going to add up to 0 because we're in equilibrium. And the sum of the forces in the perpendicular axis are going to add up to 0 because we're in equilibrium. Here we go, parallel axis. We decided to call uphill positive, so I'll be doing forces uphill minus forces downhill. This is where we use plus and minus to show direction, is in this step. Okay, so we do uphill minus downhill. Uphill I have F push cosine 20. Downhill I have this kinetic friction. So I'm going to do minus because it's going downhill. And downhill I have Fg sine 20. Together, those are going to add up to 0. Man, am I going to have enough space to put this other equation in here? Ooh, I'm going to have room on my board here. Okay, next, let's go ahead and write the sigma F equation for the other axis. Man, that is going to be ugly. Well, I'm going to try to squeeze it in there anyhow. We'll do out of the ramp minus into the ramp. Out of the ramp, I've got this normal force, and I'm calling out of the ramp the positive direction, into the ramp the negative direction. So I'll have the normal force. I feel bad squeezing this in here. Oh well. Normal. Going into the ramp, I've got these two. So it'll be minus F push sine 20. And minus Fg cosine 20. And those should add up to 0. All right. So there's my equations. Okay. This is a big deal to us getting to this point. We did a ton of physics getting to this point, thinking about what forces are acting and choosing coordinate systems and coordinate axes and so on. And the point is, at this point, from here on out, there's very little physics left. It's almost all algebra. So the physics is almost done. All right? So we will always ask you to show these equations because like I said, it's a good spot to check and make sure you've got the physics and you're understanding what's going on. We'll always ask for the sigma F equation, some of the forces equation for each axis for each system. We'll always want to see this with the labels from the diagram. The only numbers in there being angles. Okay, we always want to see label these things with variable names. Okay, even though they told us this was 200, please don't label this 200. Label it force push. Okay, and so on. Alrighty, there we go. Okay, now, like I said, it's pretty much algebra from here on out. Do we know the sizes of any of these variables? You say, well, yeah, we know force push is 200. You say, well, fine, if I know force push, that still leaves me two variables in this equation I don't know. If I know force push is 200, it still leaves me two variables here. But there is one last little bit of physics we can use, and that's the other formula for this unit. That's the formula for the gravitational force. So we have this formula that gravitational force is 9.8 newtons per kilogram times the mass. And they told us the mass was 25. We'll use that to find the gravitational force. Then I'll know this variable and this variable I can solve for the friction. I'll know this variable, 200 newtons, this one, the weight, and I can find the normal force. And then I'll have all the forces in the problem. So let's go ahead, and I usually like to just insert the calculation immediately in the lines here, rather than doing it off on the side. So let's do it that way. So here we go. So yeah, let's go ahead and do that. So force push, you know what? I'll go ahead and I'll put my values in now. If it makes a lot of people feel more comfortable if I put the values in right away, I'll go ahead and do it that way this time. So force push is 200. That friction force we don't know yet. Now the gravitational force, the formula for the gravitational force again is 9.8 times the mass. In this case, the mass is 25. So that'll give me my gravitational force right there. Yeah, and because in this problem we specifically want you to list out all the forces, we're going to end up having to do that calculation separate. Okay, and then here we've got normal minus, and then that F push we know is 200. And then that gravitational force is going to be whatever value we calculate here, right? Cosine 20 equals 0. I guess that went off camera. Equals 0, okay? All right, there we go. Okay, looking at this. At this point, I'll go ahead and I'll reach for my calculator. I'll just go ahead. Let's go ahead and just get that gravitational force because they want us to find each force individually. So 9.8 times 25. Our gravitational force is 245 newtons, okay? And that's going to be the same value here. Okay? And that's one of the forces we're supposed to solve for. So that's one thing done, okay? We're supposed to solve for the size of all of the forces. Force push, we know is 200, it was given. Now we know this one, Fg is 245 newtons. We just got two left to solve for, normal and friction. Look, I can find the friction force right here. Okay? I would just rearrange this to get friction by itself. Look, friction's being subtracted from this side. Let's just add friction to both sides, move it to the other side. And I'll have 200 cosine 20 minus that 245 sine 20 will equal that kinetic friction. I just punched out my calculator, no big deal. 200 cosine 20 minus 245 sine 20. And my calculator tells me it's 104.1 newtons. Okay, and that's that one solved for, right? This was the gravitational force. That's that one solved for. So we got, okay, so now we have force push, friction, and gravitation. Just one left to solve for. Normal force, okay, that's in this equation. Again, I want to get normal by itself, so I'll just move these other terms to the other side. I'll just add them both over to the other side. And so I'm just going to come down here if that's okay with you. There we go. And so I'll just have, hey, that normal force is going to be able to move this over 200 sine 20 plus, because I'm adding both over, 245 cosine 20. Okay, punch that in my calculator. And I get 298.6 newtons. Okay, we always know forces are in newtons. Hey, that's it. That's the problem solved. Yeah, and again, it's just a sequence of steps we go through every problem, pretty much, solving equilibrium problems. Choose your system. Do your force diagram. Getting the forces, you use a sequence of questions, right? Okay. The sequence of questions, first what range forces are acting, then for contact forces, list everything touching, and for each thing touching, you ask, are they being pressed together? If they're pressed together, there's a normal. If there's a normal, then you ask, are they trying to slide past each other? If so, there's a friction. You do that for each thing touching. If there's a rope or a string or a wire or a chain or a cable, if it's under stress, we call that a tension. And tension force always goes along the rope and pulls away from the system. And then they'll have all your forces. Then we choose coordinate axes. First axis goes along the motion. Other axes are perpendicular. Any forces going along more than one axis, we split into components using sines and cosines. And then we just go ahead and we do our similar forces for each axis. If we're in equilibrium, those forces will add to 0 in that axis. And after that, it's pretty much just algebra, right? The only physics we did here really, after this point, was this equation for calculating the gravitational force. That was it. That was it. Again, be careful about mass versus gravitational force. Masses are in kilograms. Gravitational force will be in newtons and be a force, and you got to be able to convert with that equation. The term weight, again, is a synonym for gravitational force, and weight would be in newtons also. This is the weight of the object. Gravitational force from the Earth is also called weight. Okay, that's it. That's that review of that problem. Hey, there's another review problem, and we'll take care of that in another video.